All right, we're going to go through the discussion questions for Chapter 14, Simple Harmonic Motion. Start with number 3. So number 3 gives you this little graph. Note, of course, that's a position graph of something oscillating. And it says, at what time or times is the particle moving to the right at maximum speed? So you may notice this doesn't look like the typical cosine graph that we usually start with. That's the formula you have in your formula sheet for the position of something oscillating. Usually we base it off of a cosine graph. But when we do that, we also usually say that little phase shift there, that phase constant, is 0. So, you could have a phase shift of pi or anything else and just have that same cosine graph shifted over. So, this looks like a cosine graph, but it's just a little shifted. So, anywho, it's not going to be our exact scenario of pulling the mass all the way to the right, letting it go all the way left, and all the way back right. But at any rate, we can still figure this out. So at what time or times is a particle moving to the right at maximum speed? All right. Well, when is it moving to the right at all? Well, these are positive position values. So this is moving, positive, positive, positive. That's my max positive amplitude. So right here, again, is really like where we're starting. Alright, then my position is less and less, but still positive. 0, like sort of the equilibrium position, and then down to my most negative amplitude, which would be like right there. And of course, that spot would be at the equilibrium position. So, where is moving the fastest and to the right? So I know it's moving the fastest at the equilibrium positions. So that's where the graph would be 0. So here, 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 all those times are where there'd be the max velocity, max speed. But which one's moving to the right? Well, this one was in the positive direction, now it's going negative. So it's not here. This one, however, is in the negative direction right now, passes through the equilibrium position, is now moving in the positive direction to the right. So 4 is an answer. Also 0 would have been an answer. And then same shape over here, 8. So that would be maximum speed to the right. At what time or times is the particle moving to the left with maximum speed? Again, should still be where my amplitude is 0. Maximum speed, again, is at the equilibrium position. It's right smack in the middle. So, let's see. So that will be 2, because we are, the mass is in the positive direction, the right-hand side, passes through equilibrium and is now going left, the negative side. So here, and again, and also slope is velocity. So that's a negative slope, that's a negative slope. I guess that's it. So 2 and 6. And at what time or times is a particle instantaneously at rest? It's at rest at its endpoints, when it's stretched the farthest to the right or compressed the farthest to the left. So when it's at its amplitude positions, all of these will just be moments where it's at rest. So 1, 3, 5, and 7. All right, we're going straight through to 12 and then just a couple others. A tall building is swaying back and forth on a gusty day. The wind picks up and doubles the amplitude of oscillation. By what factor does the maximum speed of the top of the building increase? And also the maximum acceleration. So a lot of these next little set of questions are formula driven. You got to be able to find the right formula that relates these factors. So amplitude is doubled. We're talking about maximum speed. And also maximum acceleration. Maximum speed was the formula omega A. And omega was 2 pi over t, if you knew the period. But it doesn't say any of those things change. So if the amplitude doubles, velocity doubles, amplitude doubles, acceleration doubles. Those things were directly related. Number 5. A child on a swing, gently swinging back and forth with a maximum angle of 5 degrees. A friend gives her a small push, so now she swings with a maximum angle of 10 degrees. By what factor does this increase her maximum speed? So this is essentially saying the same thing. I've doubled the amplitude, so I am going to double the max speed. 6. A block oscillating on a spring has an amplitude of 20 centimeters. What will be the amplitude if the maximum kinetic energy is doubled? Okay. Next set, a little trickier than just saying doubled. A little room. Okay, so I'm just going to set up sort of the original scenario, original information. Block has an amplitude of 20 centimeters. I can really relate that to potential energy. But I know that also equals maximum potential energy would equal the maximum kinetic energy. Just happen at different moments. And the maximum potential energy is 1/2 K A squared for the amplitude. That would be your X. So originally I've got, I don't know, some kinetic energy max is 1/2 K times 20 squared. That's sort of the original setup. I don't know these values. I don't actually know what the kinetic energy is. I don't know what the spring constant is. But I'm still using the same spring, so it'd still be the same spring constant. So what will be the amplitude if the maximum kinetic energy is doubled? So if I have So I want to solve for A. What's going to be the new amplitude to give me double all of that, double the original kinetic energy. So you sort of plug that in over there and solve for A. So I've got double 1/2 K 20 squared and again I'm solving for A. So a bunch of things are going to go away. I've got a 1/2 and a K on each side. Don't need that. Don't need that. So really I've got 2 20 squared A squared and then just square root. All right. Alright, so A would be really 20 times square root of 2. About 28. Okay, so in this case I was actually plugging in my original kinetic energy because I was supposed to double it. Number 7, similar but a little different approach. Alright, so in 7 it says a block oscillating on a spring has a maximum kinetic energy of 2 joules. What will be the maximum kinetic energy if the amplitude is doubled? So again, originally, so that's true originally. Again, I don't know what K is, nor do I even know what A is, but the kinetic energy is 2, and it would equal 1/2 kx squared. And I'm using that, I know that's the potential energy formula, but the max kinetic energy would equal the max potential energy, and I'm using the potential energy formula because that one has amplitude in it. So what will be the maximum kinetic energy if the amplitude is doubled? So K nu sorry, 2A. So what's my new kinetic energy if I double the amplitude? If I double the amplitude, because it's squared, you have this factor of four. So my new kinetic energy is really 4 times the old. Because if you look at this, you know, other than the 4, I've got 1/2 Ka squared, and that is 2. So the 1/2 Ka squared part is 2. I'll say K old. So you should get 8 joules. That's kind of doing it all out. You can maybe more quickly just notice that kinetic energy is based off of amplitude squared. So if you're going to double that, that's going to give you a factor of 4 when you square that 2 factor there. So it should be 4 times bigger. All right. Alright, number 8. A block oscillating on a spring has a maximum speed of 30 centimeters per second. What will be the block's maximum speed if the initial elongation of the spring is doubled? Okay, so we just had a question very similar to that. Maximum velocity formula is at omega times amplitude. The initial elongation of the spring is doubled. That's just saying you are doubling your amplitude. So if you're doubling the amplitude, you're going to double the max velocity. So that should be 60. Okay, let's scroll down the graph. All right, number 9, graph questions, great to understand for simple harmonic motion. All right, so it says determine the frequency and the amplitude based off of this graph. Well, it is a position graph, so amplitude is very easy. Amplitude is just the max displacement, so amplitude's got to be 10 centimeters. Frequency doesn't directly tell me, but I know frequency is related to period. And hopefully you remember what period means. Period is the time for one full cycle, time for one full oscillation. So, yeah, we're starting here about 5. You know, where do I get back to that spot? Where have I done a full motion, the up and the down of your trig function graph? So gone down, back up, back down. You know, that's one full motion. So that's 2 seconds is the period. It takes 2 seconds to do a full cycle. So the frequency would be half a hertz. Different graph. Note, of course, that this is now a velocity graph, not position. So determine the frequency and amplitude. Frequency, still the same thing. Figure out your period. Even though it's a velocity graph, I'm still looking to see where the motion repeats itself. So again, we'll start here. Looking like it's about 2 seconds to do a full motion. So if the period is 2, frequency is again half a hertz. Does half of a cycle in 1 second. All right, amplitude A. Amplitude I can relate to velocity with my max formula. I know the max velocity is 10, but I do need to know what omega is. And omega is 2 pi over t, just another formula we need to know. This is sort of like the angular speed. You know, I'll do one full cycle in one full period's worth of time. And we knew the t was 2, so 2 pi over 2. Sorry, it's supposed to be pi. So omega is pi. So I've got 10 centimeters per second equals pi a. So you divide by pi, you get your answer in centimeters, but that's all right. 10 divided by pi. About 3.2 centimeters. All right, 11 and 12. Block oscillating on a spring's got a period of 2. Like we just sort of saw. What's the period if the block's mass is doubled? All right, now we're going to talk about spring constant, amplitude. So it might be helpful to think of a formula that involves mass and period. So this is already set up to solve for period. That's the period formula for a mass spring system. You need to memorize that. Get in the calculator. So what's the period if the mass is doubled? Well, if I throw in a factor of 2 here, I throw in a factor of 2 for the mass, note that it is under the radical. So I really am changing my period by a factor of square root of 2. So if the original period was 2 seconds, you know, like all of this red equaled 2 seconds. Well, this blue looks exactly the same, except I've got that square root of 2 in there. So T new is square root of 2 times 2. Or about 2.8 seconds. If you think about, you know, what is physically happening, so you've made, it's the same spring, but you put a heavier mass on the end of it, it should make sense that it would be a little slower, or take longer to pull that mass all the way left and go back all the way right. So period would increase, it would turn to 2.8 seconds. All right, what if the spring constant is quadrupled? So I'm throwing this factor of 4 in the denominator, but it's still under my little radical. So if I quadruple k, how does that change t? Well, you can kind of see, you know, square root of 4 is 2. But it's in the bottom of the fraction, so I'm going to have to pull out that as a half. So by throwing in that 4, I've changed the period really by half of what it was. So half of 2 would be 1 second. What's the period if the oscillation amplitude is doubled, where m and k are unchanged? All right, that is a pretty common question. I feel like I've seen that on most AP tests. A question about amplitude and period, because students often think you take that spring and you stretch it twice as far to the right that it's going to change the period. And you might think it would take longer. I mean, it's got farther to go now. But while it does have farther to travel, if you stretched it twice as far, the force is twice as great. So you have extra force. It's going to be pulled harder to the left if you pull it twice as far. So note that amplitude is not in this formula. The amplitude does not affect the period. If it takes 2 seconds, you pull it, 5 centimeters, it's still going to take 2 seconds even if you pull it a meter. It's just going to snap back way faster because it's got more distance to travel. So the period is actually unchanged if you change amplitude. All right, 12. A pendulum on planet X, where the value of g is unknown, oscillates with a period of 2 seconds. Okay, so that was the period for a spring. You also know the period for a pendulum formula. So what's the period of this pendulum if the mass is doubled? Also a very common question like C here. Students always think if you put a heavier mass on your pendulum, that would swing faster. But the period is not changed based on mass. Mass is not part of this equation. And unfortunately, we won't do our little pendulum lab, but we would have proved that. String length, however, the length of the pendulum definitely matters. So if its length is doubled, you again have that square root of 2 factor in there. So that's really just like saying the mass is doubled for part A here. So same math we just did. You're plugging in a 2 next to the L. You're doubling the L. That gives you an extra square root of 2 value. So square root of 2 times the period of 2. We just did that because that was 2.8 seconds. All right, and its oscillation amplitude is doubled. That does not affect period either. So same question as this, really. So it would still be 2 seconds. Amplitude does not affect the period. Now you got to be a little careful because we had that qualification for pendulums that you really needed a small angle for this to truly be considered simple harmonic motion, like 5 degrees or less. So in theory, we're going from like 2 degrees to 4 degrees, in which case that would be okay. But like if you're turning this into a huge angle, then it's really not simple harmonic motion anyway. All right, 14. Denver is at a higher elevation than Miami. The free fall acceleration is slightly less. If a pendulum clock keeps perfect time in Miami, will it run fast or slow in Denver? Well, if G is smaller in Denver, higher up, so if I've got a smaller denominator, then the overall fraction is a bigger answer, bigger value. So a small denominator is going to make this a bigger value, and therefore just make t itself bigger. So it's going to take more time than it should to be the same time, or to be whatever time it's supposed to be. So it's going to take more time than it should. That means it's running slow. Okay, 2 more problems, 23 and 25. Multiple choice again. Find an equation that helps you answer these. A spring has an unstretched length of 20 centimeters. A 100-gram mass hanging from the spring stretches it to an equilibrium length of 30 centimeters. So equilibrium, that's going to be at rest. So really this is kind of irrelevant. I don't really care what the spring is doing without that mass on it. It says, suppose the mass is pulled down to where the spring's length is 40 centimeters. When it is released, it begins to oscillate. What is its amplitude of the oscillation? Well, if it's at rest at 30, you pull it down to 40, it would snap back up to 20, but we would say the amplitude is, again, the displacement considering the equilibrium position to be 0. So if the equilibrium position is at 30, it just went down 10 centimeters. So amplitude is 10. What is the frequency? All right, well, I know frequency is 1 over t. Let's see. Yeah, okay. Do I have K? I don't have K. Alright, so I'm trying to think of what formulas I have that can help me with finding the period. So I've got the 2 pi square root of m over k, but I don't know k. So not that. Oh, but I can't find that. Okay. Sorry, I was looking for either maximum speed or something like that. Alright, let me go back to the other one, sorry. Okay, so I can find the frequency if I can find the period. I can find the period if I just know the mass and the K, the spring constant, which I can figure out just by knowing sort of the restoring force. If I know that it is an equilibrium here, I know that the spring force up equals the weight down. And spring force is Hooke's law, Kx, and weight is, of course, mg. So mass, let's go back to kilograms, so 0.1 times 9.81 divided by, conveniently 0.1, for my x. My displacement was 10 centimeters. So that means K is 9.81 newtons per meter. So now I can plug in over here. My mass again is 100 grams, but put in 0.1. So 0.1 divided by 9.81 square root and times 2 pi. So my T I get about 0.63 seconds. So 1 over that is 1.58, 1.6. So that's got to be C. Notice that the point, I got 0.63, but they have 0.62 as a choice. They probably didn't use 9.81 exactly as gravity, but careful, because that's the period. You want the frequency. You just have to do 1 over that. Okay, suppose this experiment were done on the moon, where free fall acceleration is approximately 1/6 of that on Earth. How would this change the frequency of the oscillation? Well, we got to go back through what we just did. We said Kx well, I mean, that would change the displacement. But it wouldn't change the spring constant. So since the displacement does not affect the period, then the frequency should not change. And it's still the same spring. It would still be the same spring constant even if we went to the moon. Even if G is different, that's okay. So gravity is really not part of that period formula. So only the mass, only the spring constant would matter. I know that we use gravity to solve for the spring constant, but that also involved amplitude. Amplitude would be different too. So in the end, it wouldn't change. Okay, last one, 25. Alright, I like this one just because we haven't really seen one of those equations in the discussion questions here. So this one says, ball of mass m oscillates on a spring with spring constant 200 newtons per meter. The ball's position is 0.35 meters times that cosine function, t is in seconds. Alright, what's the amplitude of the ball's motion? Just remember the original formula. You know, there could have been that plus, like, phase shift there, phase constant, but that's obviously 0 here. So what's the amplitude of the ball's motion? Well, it's just whatever is in front of cosine. So the 0.35 is your amplitude. What is the frequency? All right, again, if I want to do frequency, I need t. Now, I could get t if I knew m and k. I know m, or I know k, but I don't know m. So close, too. Alright. So t. The other formula you know for t is 2 pi over omega, and omega is what is in front of the time. So our omega here is 15. So we'll figure out our period. 2 times pi divided by 15 is 0.42. And then 1 divided by 0.42 is 2.38, 2.39. So gotta be B. Alright, note K is 200. I just want to leave it where I can see the given information. Part C says, what's the mass? And I wonder if I can bring back what I just had. Okay. So we have mass, energy, Vmax. Okay, so part C says, what is the mass? I know I can relate period to m and k. Also, you have this equation anyway. Which I'll just skip to that because I know omega is 15. Square root of 200 over m. So let's say I'll square the other both sides. 15 squared is 225, and then 200 divided by 225 gives me a mass of 0.89. kilograms. Hopefully that was a choice for C. We'll check in a second. Actually, let's just make sure. Yeah. Okay, so 0.89 kilograms is the mass. Total energy. If I knew the total speed, I could do max kinetic, 1/2 mv squared. But I don't know that yet. I'll get it from here. So I'll just use my max potential formula. One half Ka squared, and we already just said that the amplitude was 0.35. So 0.35 squared times 100. About 12.25 joules. So that's the maximum kinetic energy, that's also the maximum potential energy, that's also the total mechanical energy. And this is definitely not the only way you could get V max, but since we just used energy, I'm going to say that max kinetic is also 12.25 joules. You also have Vmax is omega times amplitude. We have found omega, we can multiply that by 0.35. Either way, should get the same thing. Alright, so we have 12.25 times 2 divided by 0.89 and square root. So let's just double check that those are choices. Yeah. So 12.2 was a choice for my energy and 5.25 for my velocity. Okay, that is the end of the discussion questions for simple harmonic motion.